Hello there and welcome back to the Sleep Science. So you're already floating in it, whether you know it or not. Imagine this, you're walking through your kitchen at midnight, toes cold on tile, reaching for a glass of water, harmless enough. But as you pour every droplet, every glint of light on the rim of the glass, even the quiet tension of your muscles, is rooted in a universe that doesn't behave. It doesn't obey. It barely makes sense. You're standing on the crust of something very strange, and tonight we're diving under it. Quantum physics is the science of the teeny, the twitchy, the slightly possessed. Down here, particles forget they're particles. They overlap. They vanish. They disobey orders. And everything you thought you knew about space, time, cause, and effect starts to crack. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you're cozy already, drop your location and what time it is where you are. Let's see how many universes we're in at once. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You open your eyes, but instead of a room, you find yourself suspended in something that isn't quite a vacuum and isn't quite a storm. It hums, not with sound, but with probability. This is the quantum world, a place so small that even atoms feel bulky. A place where nothing is stable and everything is uncertain. You reach out tentatively and your hand passes through what looks like a glowing dot. The dot responds by becoming a wave, which then splits into several waves. One of them seems to ripple toward you, another retreats, and the rest just sort of vibrate. Congratulations. You've just met a quantum particle. Not to scare you right out the gate, but you probably won't survive this. Not because it's dangerous, but because logic gets shredded down here. You can't rely on it. In this space, the rules are more like guidelines that particles follow only when someone's watching, and even then, not very well. You drift past a floating blackboard where scribbles of wave functions swirl like animated chalk. You squint, trying to focus on one of them. The letters PIS, Persei, shimmer with math you don't recognize. That little symbol represents the quantum state, mathematical ghost of all the possible things a particle might be doing. It's not telling you what is, only what could be. That's the first lesson here. At the quantum level, possibilities matter more than realities. And here's the kicker. Reality as you know it doesn't actually solidify until someone measures it. You start to see familiar shapes now, a hydrogen atom. It's one electron doing a lazy orbit around the nucleus. Except it's not orbiting. Not really. The electron exists as a kind of fuzzy cloud, like a rumour of itself. Not in one place, but in many. The idea that electrons spin around like little moons is charming, but wrong. They smear. They flirt with location, never committing. If you try to look, it'll pick a spot and pretend to have always been there. That alone would keep most people up at night. But wait, it gets worse. Historians still argue whether quantum theory emerged purely out of desperation or a stroke of deranged brilliance. It started in the early 20th century, when classical physics failed to explain some unsettling experimental results. Like, why did hot objects emit radiation in specific patterns? Why didn't electrons spiral into their nuclei and implode atoms left and right? The math wasn't adding up, until physicists like Planck, Einstein and Bohr started treating energy not as a smooth stream, but as packets. Little quanta, discrete, choppy, and extremely annoying. We're not here for the equations though, we're here for the vibe. And the vibe is you are not in control. As you float farther in, the world around you becomes even more fluid. There are no clear edges, no solid lines. Objects wink in and out of existing. You catch glimpses of particles jumping from one place to another with no path between. A flash, then nothing, then a flash again. They call it a quantum leap, but it's nothing like the TV show. These leaps ignore space entirely. It's like teleportation, if teleportation had no concern for how or why. A grainy old radio floats by, tuning itself to static. You hear a voice crackle in. If you think you understand quantum mechanics, you don't. That's Richard Feynman, the rock star of quantum theory. He laughed at how absurd it all was, and then went ahead and built the foundation of quantum electrodynamics anyway. He also played the bongos, so draw your own conclusions about the side effects of working in this field. Near the edge of your vision, something stirs. It looks like a bubble at first, then a ripple, then a spark of light that's immediately gone. It might have been a virtual particle, a phenomenon you don't notice in regular life, but one that may very well be propping up the entire universe. These ghost particles emerge from empty space, flirt briefly with existence, and disappear again, borrowed from the vacuum itself. Fringe theorists joke that reality is over-leveraged on quantum debt. And if you're wondering how all of this doesn't just crumble into chaos, well, good question. Physicists have found ways to predict behaviours with stunning accuracy. Quantum theory isn't a guess. It's the most precisely tested framework in all of science. Lasers, GPS, semiconductors, MRI machines, none of these work without quantum physics. So as bizarre as it all sounds, it's not magic. It's just rude. You finally reach what looks like the bottom. There's no flaw, but you feel a stillness here, like the particles have stopped trying to impress you. You're in the heart of the quantum realm now, and this is where the rules of classical logic officially give up. Welcome to the place where things can be two things at once, where nothing happens until someone notices, where causality is a polite suggestion, not a mandate, and you're just along for the ride. The box is simple enough. Just a dull, unmarked cube sitting quietly in the middle of a shadowy corridor. It doesn't hum, it doesn't glow, it doesn't even cast much of a shadow, but you already know this isn't any ordinary container. You step toward it, hesitating slightly as you reach out because you already know what's supposedly inside. And let's be clear, you're not emotionally prepared for it. The cat, that cat, you're not sure whether you'll find a curious purring fluffball or a silent, unmoving feline tragedy. But here's the thing, until you open the box, it's apparently both. That's not poetic exaggeration. According to the bizarre logic of quantum physics, Schrödinger's cat is simultaneously alive and dead. And you're about to become part of the crime. Erwin Schrödinger, an Austrian physicist with a deeply uncomfortable moustache, cooked up this scenario in 1935. Not to celebrate quantum weirdness, but to mock it. He found the idea of a system being in two opposite states at once utterly ridiculous. So he built a mental trap, a sealed box containing a cat, a tiny amount of radioactive material, a Geiger counter, a hammer, and a vial of poison. If the radioactive atom decays, which is a purely random quantum event, it triggers the Geiger counter, drops the hammer, breaks the vial, and, well, goodbye whiskers. But if it doesn't decay, the cat lives. And because that decay is governed by quantum rules, it exists in a superposition, a mixture of decayed and not decayed, until someone checks. So the cat becomes a grim cocktail of alive and dead. Only when you open the box does it choose a state. That's the quantum world's version of customer service. You don't get a result until you press the help button. You kneel beside the box now, heart thudding softly in your ears. And just for a moment, you imagine it not as a metal container, but as a philosophical landmine. A trap built not with wires or explosives, but with pure uncertainty. If you peek inside, you collapse the quantum wave function. If you don't, it just keeps on vibrating in limbo. Historians still argue whether Schrödinger was trying to break quantum mechanics with this thought experiment, or simply trolling his colleagues at the Copenhagen school. Bohr and Heisenberg, the rock stars of the Copenhagen interpretation, insisted that quantum systems don't have definite properties until measured. Schrödinger found this absurd. So what, he essentially asked, we just treat a cat as half dead until someone checks. Unfortunately for him, and for the cat, the math backed up the madness. You lift the lid slowly, your breath catches, there's nothing inside, no cat, no poison, no hammer, just an airy shimmer of potential, as if the system refused to resolve itself in front of you. A soft hum of possibility lingers where reality should be. It's almost mocking. You were expecting closure. Instead, you got a riddle. And that's the dirty secret of this experiment. The cat isn't the main point. You are. More precisely, your role as an observer. Because in quantum mechanics, the act of observing something doesn't just reveal its state, it defines it. Before that, it's all blurred probabilities, existing in all forms at once. Alive and dead, spin up and spin down, present and not. You step back from the box, mind spinning. A wave of nausea passes through you, not from horror, but from the realization that reality is more polite fiction than hard fact. The cat story is gruesome, yes, but it's a metaphor for something deeper. The instability of truth itself at quantum scales. Somewhere behind you, a dusty museum placard flickers to life. It shows another box, this one transparent. Inside, a radioactive isotope suspended between two magnetic fields. Scientists have actually done versions of this experiment. With particles, not pets, don't worry. They've seen atoms hold conflicting identities until measurement. Quantum superpositions aren't just theory anymore, they're observable. The cat story was absurd until it wasn't. That leads to the next uncomfortable twist. What qualifies as a measurement? Is it a lab sensor? A pair of human eyes? A cosmic ray? A consciousness? Physicists still haven't agreed. Some say anything that entangles the system with its environment counts. Others argue that awareness plays a role. Fringe theorists have even dragged in the idea that your mind itself may be collapsing the wave function, that the universe changes because you noticed it. A flattering idea, if also mildly terrifying. To distract yourself, you drift toward a nearby viewing screen. It plays a looping animation of particles entering quantum superposition, decohering and collapsing into classical states. It's oddly beautiful, like a choreographed dance of probability and certainty. The music in your head would be ambient jazz, if jazz had an anxiety disorder. Let's detour for a second. Did you know that in 2000, researchers actually created a superposition involving a macroscopic object, a tiny mirror, by cooling it near absolute zero and suspending it in two vibrational states at once? Not a cat, sure, but not nothing. The boundary between small enough to be weird and big enough to behave is fuzzier than we'd like to admit. The box is gone now, fading into the distance like a dream you'd rather forget. And still, the question echoes. When does potential become real? When do things stop existing in possibility and start existing, in fact? You wander through a corridor lined with chalkboard graffiti, mathematical equations looped in spirals, corrections scrawled sideways, some of them in Latin, others in cartoons. There's a crude drawing of a cat with devil horns labelled superpossession. And then, just to drive home how little you actually know, you remember this. Quantum particles routinely interfere with themselves. They behave like they're taking every path, every state simultaneously, until someone checks, and they can entangle, meaning two or more particles can share a single wave function. Alter one, and the other responds instantly, even if it's on the other side of the galaxy. You shiver, not from cold but from awe. This isn't just physics, it's a trust fall into chaos. And yet, ironically, it works. GPS satellites wouldn't function without compensating for quantum time shifts. Lasers rely on stimulated emission, a quantum phenomenon. Even your phone owes its brainpower to transistors born in the bowels of quantum mechanics. The cat, dead or alive or both, isn't the problem. It's just the messenger. A furry ambassador from a realm where logic wobbles and observation is everything. You never found it in the box, but in a way, it found you. You take another cautious stare through the ever-shifting haze, and this time you feel it, like trying to hold water between your fingers. Something wriggles out of your mental grip. You blink and try again to focus. There's a particle, yes, just one, hovering right in front of you, pulsing gently like it knows it's being watched. You stretch out your hand trying to catch it, or at least guess where it is, but the moment you try to measure its location, its momentum slides away like a soap bar in a hotel shower. When you focus on its speed, its position turns into a fuzzy blur. Welcome to the Heisenberg uncertainty principle. And no, it has nothing to do with Breaking Bad, though it would make an incredible band name. What you're experiencing is one of the most stubborn and foundational rules in quantum physics. It tells you that you can't know both where a particle is and how fast it's going. Not precisely, not at the same time. You can pick one, sure, but the other will slip through your fingers. The universe, it turns out, has a built-in privacy filter. Reality is fuzzy by design. Werner Heisenberg, yes, a real guy. And no, he didn't cook meth. Published this idea in 1927, flipping the scientific world on its side. It wasn't that measurement tools weren't good enough. It wasn't that physicists needed more sensitive equipment. The uncertainty wasn't a flaw in the process. It was the process. Deep down at the quantum level, particles don't have sharp, definite values until forced to settle. Like you choosing your mood when someone asks how you're doing. Fine, I guess, even if you were feeling 6 different ways at once. Historians still argue whether Heisenberg's idea reflected something truly fundamental about nature, or if it was a side effect of the way we model systems using wave functions. Either way, the math works, and reality keeps behaving like it's got something to hide. You float closer to the particle again. This time you try something sneaky. You observe it without really observing. But quantum physics has a nose for intention. As soon as you try to know, the universe reroutes itself. You end up with incomplete data and a mild existential crisis. This isn't just about tiny invisible particles. The uncertainty principle has real consequences for everything from atomic structure to the way stars burn. In fact, it's the reason electrons don't crash into the nucleus of an atom and obliterate the whole thing. If an electron got too cozy in the center, its location would be known too precisely. The rules would demand an infinite uncertainty in its momentum, causing it to rocket off unpredictably. So it stays in a soft cloud around the nucleus, uncertain enough to stay safe, like a house cat that only cuddles when you're not looking. Here's a lesser-known twist. The uncertainty principle also places limits on time and energy. The more precisely you measure one, the blurrier the other gets. That's why virtual particles can momentarily appear and vanish without breaking the laws of physics. They borrow energy from the vacuum but repay it so quickly that the universe just shrugs and looks the other way. You land on a ledge that wasn't there a moment ago. On it, there's a cracked leather-bound notebook filled with scribbles, half math, half desperate poetry. One page reads, "I saw the position, and the momentum recoiled like a lover caught lying." You chuckle softly. Whoever was here before you understood, or at least they tried. And it gets weirder. You've heard of quantum tunneling. It's a close cousin of the uncertainty party. Because of these blurred boundaries, particles sometimes appear where they shouldn't be, through barriers, inside forbidden zones, as if they got tired of the rules and slipped through a crack. The uncertainty principle gives them just enough wiggle room to cheat fate. You stroll through what looks like an old subway platform made of starlight. Projected above you is the famous Heisenberg microscope thought experiment. Imagine trying to observe an electron with a photon, say, light bouncing off it. To see it clearly, you need a high-energy photon, but using one disturbs the electron's momentum. Use a gentler photon and you don't disturb the momentum, but you don't see much either. You're trapped in a feedback loop of uncertainty. Physicists still debate how much of this is about knowledge versus reality. Are the particles really uncertain? Or is it just us, looking with imperfect tools into a weird mirror? Some interpretations argue the fuzziness is all in the wave function, a probability cloud, not a literal one. Others insist nature really is this blurry. No hidden gears, no deeper truth, just smeared out maybes. A faint rumbling interrupts your thoughts, the walls around you dissolve into swirling light and you're falling again, though falling isn't quite right when up and down don't exist anymore. Around you, snippets of classical physics shout in protest, equations crumbling into question marks as they pass. Newton would be screaming right now, or maybe laughing nervously while sipping tea. You land gently in a library. No, a museum. Each display case holds a particle caught mid-squirm. There's a small plaque near one. Quark, location probability 72% within this chamber. Speed, vague. You move on. Another says, Mon, fast, furious, direction uncertain. Every exhibit is a confession that nature refuses to sign in ink. Even the most stable atom, under enough scrutiny, turns coy. And then, just to mess with your sense of control, a tiny display pulses with a quote from Heisenberg himself. What we observe is not nature itself, but nature exposed to our method of questioning. You wonder how many things in your life, your memory, your identity, even your dreams, are the result of asking the wrong questions too precisely. A quirky fact for the sleep-deprived traveller: uncertainty isn't just a scientific principle, it's inspired art. There's a 60s jazz album called The Heisenberg Uncertainty Players. No joke, their songs feature deliberately unpredictable solos that never resolve. Listening to it feels like chasing your own tail through a cloud of saxophones, which, oddly enough, is a pretty good metaphor for the entire field. You exhale slowly. The rules here are strange but strangely consistent. The universe, at its smallest scales, doesn't like being pinned down. It dances out of reach, not because it's shy, but because that's its nature. And so you drift forward again, carrying a new truth. Not everything that exists can be measured, and not everything measurable can be fully known. You wake, or at least you think you do, in a room where everything flickers just slightly out of sync. The floor hums beneath your feet, but you're not sure if it's real. Objects shimmer with soft outlines like bad Photoshop masks, and every time you try to focus on one, it starts to multiply. You reach for a cup, only to find yourself reaching for 5 cups, then none at all, and finally one that's halfway through disappearing. This, dear traveller, is superposition, and yes, it feels illegal. In the everyday world, a light switch is either on or off. Your sandwich is either in the fridge or in your hand. You're either awake or asleep, except during Zoom meetings. But in the quantum world, particles don't pick sides, they don't decide. Instead, they exist in a messy, glorious mix of all possible states at once. Not because they're lazy, but because the universe, at its tiniest levels, refuses to commit until it absolutely has to. You're now inside the quantum waiting room, a place where everything that could happen is happening, until it's not. Look to your left. There's a particle suspended in space, glowing faintly. It's not here or there, it's both. It spins clockwise and counterclockwise. It goes through the left door and the right. It's in one place, then two, then everywhere. You'd call it magic, if it weren't so precisely predicted by math. You try to interact with it, but the moment you do, it snaps into a single version. Like a character freezing in a play when the audience arrives. The drama is over, the outcome is fixed. That snap, that sudden collapse from many to one, is what physicists call the wave function collapse. And if it makes you uncomfortable, congratulations, you're paying attention. Superposition isn't a theoretical quirk. It's been proven over and over, in labs so cold and quiet you can hear the hum of the refrigerator struggling to chill particles to near absolute zero. Even electrons, the tiny workhorses of atoms, routinely exist in multiple spin states at once. Photons, too, have been shown to walk through 2 doors simultaneously, until you try to check which one they used. Then they politely pick a path and erase the history of the alternative. Like a child lying with impressive commitment. Historians still argue whether the particle is in all these states simultaneously, or if the wave function is simply a statement about what we know of the particle. Is it reality itself that's indecisive, or just our picture of it? The debate splits physicists into camps: the Copenhagen loyalists, the many worlds dreamers, the Bohemian rebels. Each insist the math is right. It's the interpretation that's up for grabs. You wander into what looks like a dressing room backstage at the quantum opera. Particles hang their possible states like outfits. This one could be red or blue, that one is up spin or down spin, and some wear combinations like they've lost a bet. You realise, until someone forces a decision, all the options are equally real. It's like Schrödinger's cat again, but expanded. Not just alive or dead, alive and dead, on a diet and on its 5th mouse, playing chess and ignoring you completely. Let's go real world for a second. In 1998, scientists placed a molecule made of 60 carbon atoms called a buckyball into a superposition state and sent it through a double-slit experiment. It behaved like a wave. It interfered with itself. Not a single particle, but all possibilities at once. A molecule bigger than most viruses, performing a quantum ballet. And this isn't just a lab curiosity. Quantum superposition is the engine behind quantum computing. You step now into a room filled with glowing orbs, qubits. Unlike classical bits, which are either 0 or 1, qubits can be 0 and 1 at the same time. They hold multiple possibilities in parallel, crunching through problems the way a caffeine-soaked genius might explore 50 chess strategies before you blink. It's messy, it's delicate, it's barely stable. But if it works, it changes everything. The light around you dims, a screen lowers from the ceiling, old-school projector vibes, and you watch a grainy video of the famous quantum experiment, an electron gun firing particles through 2 slits in a wall. Behind the slits, a screen records where they land. When no one's watching which slit they go through, the electrons form an interference pattern, like waves overlapping. But when someone places a detector to observe the path, the pattern disappears. Suddenly the electrons act like polite little marbles and pick one slit. The act of measurement collapses the superposition. It's like the particles know they're being watched. And yes, we'll come back to that creepy idea later. You float past a sign labelled "Here Be Maybes." Inside, particles flit about like over-caffeinated fireflies. Each carries a banner with a probability. 70% chance it's here, 20% it's there, 10% it's doing something you can't even describe. You realise these aren't just hypothetical numbers. There are the best predictions the universe will give you. Not certainties, just odds. You rest your hand on a particle, not literally, because that would cause it to collapse, but close enough to feel its hum. It vibrates with all its unrealized futures. It hasn't chosen yet, neither have you. And in that moment you finally get it. Superposition isn't a bug, it's a feature. The universe doesn't commit because it doesn't have to. The cosmos is a slush of possibility, and only under observation does it pick a storyline. You're not just a spectator, you're part of the act. Here's a quirky bonus. The first person to describe quantum superposition formally was not Schrödinger, but a German mathematician named Paul Dirac. He wrote equations so elegant that even other physicists called them beautiful. His work predicted antimatter before it was even discovered. Superposition was just a footnote in his grander tapestry. Imagine casually inventing multiple realities before lunch. You step back, away from the shimmering possibilities, and take a deep breath. If breath is even a thing here. All around you, the world recalibrates. The flickering objects settle into single forms. The floor feels real again. You blink, and the strange dressing room is gone. In its place, a path made of quiet starlight leading forward. But just behind you, you feel a pull. Like something you didn't choose still exists. Like a version of you stayed behind, reaching for a different possibility. And maybe it did. You feel it before you see it. A tug, a tiny pull on your thoughts, like someone gently trying to turn your head towards something unspeakably distant. You turn, and there it is. Two lights hovering in the dark, faint and trembling, but unmistakably connected. You watch as one of them flickers. Instantly the other shivers in response. No delay, no hesitation, as if space itself is irrelevant. Welcome to entanglement, the most baffling long-distance relationship in the universe. At first, it doesn't look like much. Just a pair of particles, photons maybe, spinnings in opposite directions. You wouldn't even notice anything unusual, except for the fact that every time you check one, the other seems to have known what result you'd get. You measure one particle's spin, and the other instantly adopts the matching opposite, no matter how far away it is. One here, one on the other side of the galaxy, a billion light years apart but in perfect sync. You drift closer, half expecting some hidden string or wire connecting them. There's none, and yet the two act like one. It's not communication, not exactly. That would imply a message travelling between them, and that takes time. This is faster than time. It's immediate. Einstein hated it. He famously called it spooky action at a distance, and if the phrase sounds like something whispered during a séance, you're not wrong. Historians still argue whether Einstein's objections were philosophical, mathematical, or just stubborn. He believed in local realism, the idea that things have definite properties whether we observe them or not, and that nothing can travel faster than light. Entanglement laughed in his face, and to this day we don't fully understand how it works. Here's the kicker. It's real. It's not theoretical. We've tested it, over and over. In the 1980s, physicist Alan Aspect ran experiments that closed most of the major loopholes. Later, in 2015, scientists entangled photons across a Swiss village, timing the measurements so precisely that any cheating through hidden signals would have been impossible. The results? Quantum mechanics held firm. The entangled particles behaved as if space didn't matter. You now float between two glowing orbs, representing entangled particles. Each emits a gentle chime as you move. You touch one, it turns blue. Instantly the other goes red. You flip one upside down and the other mimics the corresponding inverse. It's like watching twins finish each other's sentences telepathically, even after being adopted by entirely different galaxies. But here's what really fries your sleepy brain. It's not that the particles carry secret instructions, it's not like they're pre-programmed. The measurements themselves don't exist until they're made. Each outcome pops into reality only when you check, and the other outcome pops into place across the cosmos to match. It's not just weird, it's anti-weird. It's something your brain isn't built to accept. Entanglement isn't just some quantum parlor trick either. It's the foundation of quantum teleportation. Yes, teleportation. But let's be honest, not the kind that zaps Captain Kirk across the galaxy. Quantum teleportation involves transmitting the state of a particle across a distance, not the particle itself. You destroy the original to recreate it elsewhere. It's less beam me up, more delete here, paste there. A tragic romance of information. In 1997, physicists managed to teleport a photon using entanglement. Since then, we've teleported ions, atoms, and entire packets of quantum information. In 2020, scientists entangled qubits across a fiber optic network stretching 44 kilometers. That's nearly a marathon of spooky action. There's a room now ahead of you filled with mirrors that don't reflect you, but something else. As you enter, the mirrors light up with versions of yourself reacting in real time, not copies, not reflections, entangled echoes. Each one changes as you move, but some lag behind, others anticipate you. They are not you exactly, but they know you. Or rather, they know a correlated version of you shaped by the same invisible dance. It's unsettling. You turn quickly and the reflections collapse into darkness. You wonder, if particles can be so deeply linked, what does that say about the rest of the universe? Could larger systems, molecules, cells, brains, exhibit entanglement in more complex ways? Some fringe thinkers argue that consciousness itself might involve quantum entanglement between neurons. No hard proof yet, but the idea lingers like smoke in the air. And while mainstream neuroscience isn't packing up its theories just yet, it can't fully rule it out either. A quirky fact for your quiet orbit. In 2008, researchers managed to entangle diamonds. Yes, actual diamonds, objects composed of billions of atoms. They vibrated in perfect sync, like two singing crystals across the room from each other, sharing a silent harmony no one could hear. It wasn't just symbolic. It was a hint that maybe, just maybe, quantum weirdness doesn't end at the microscopic scale. Still, there's a catch. Entanglement doesn't let you send information faster than light. You can't use it to call your alternate universe friend or cheat at interstellar poker. The outcomes are random. You only see the correlation after comparing notes. So the universe teases you, showing connection without causation, coordination without communication. You pause now at the edge of a cliff that hangs over nothing, just swirling probability. The entangled particles float beside you, patient. You reach out to one again. This time it splits. The twin does too. Now there are 4, then 8, then a blur. You're surrounded by the ghostly multiplication of possibility. Every measurement you might make explodes into a branching consequence. This isn't just a connection. It's a fractal of cause and effect tied together with invisible string. And suddenly you understand why entanglement scares even seasoned physicists. It's not just spooky, it's invasive. It tells us that isolation is an illusion, that anything that's ever interacted may still be whispering to its twin, even across the light years. A subtle tap on the shoulder from across space-time. As you turn to walk onward, the 2 original particles dissolve, leaving behind a faint note in the air. It hums with something you can't quite explain. A presence, a consequence. Maybe it's still watching, maybe somehow so are you. You're walking now, at least it feels like walking, though the ground beneath your feet ripples like liquid, and the air shimmers with uncertainty. Ahead there's a stone wall, rough, textured, ordinary looking. A comforting bit of classical physics in this otherwise quantum mess. You're handed a small object, smooth and metallic, a particle, or something close to one. You're asked to toss it at the wall. You do. The particle hits the wall, except it doesn't. It passes through and leaves behind something impossible, an interference pattern. You pause, you blink, you try again. This time you throw a single particle, just one, and instead of a single dot where it landed, you see a wave pattern begin to form on the far side. Not because it bounced, not because it split in two, but because it interfered with itself, as if it somehow went through both sides of the wall, like a ghost trying doors it hasn't decided on yet. Welcome to the double-slit experiment, the one that broke reality. It sounds innocent. A simple setup. 2 narrow slits in a screen, a source that fires particles, photons, electrons, even molecules at the slits, and a detector wall that shows where they land. If you just watch the results, it looks like waves interfering, like water ripples overlapping and cancelling each other out in places. But here's the madness. If you fire the particles one at a time, even with minutes or hours in between, the same interference pattern still builds up. Each particle is somehow behaving like a wave, like it goes through both slits, like it interferes with itself, until you measure it. The moment you add a detector to see which slit the particle actually passes through, the interference disappears, Gone. The particles now land like classical bullets. No wave behavior, just two blobs behind the slits. Somehow the act of observation collapses the weirdness. The system suddenly decides to behave like a particle. It's not just spooky, it's rude. Historians still argue whether this experiment marked the true fracture point between classical and quantum physics. Thomas Young originally did the double slit experiment in 1801 with light, to demonstrate that it behaved like a wave. But it wasn't until the 20th century that scientists started trying it with electrons and even molecules. And that's when reality started to frown. You stare at the two slits now floating gently in space, bordered by glowing quantum graffiti. Choose, but choose wisely. You toss another particle. Again it seems to pass through both slits, interfere with itself, and land on the far wall in a pattern no single dot could predict. But many dots do over time. You're not just watching physics, you're watching possibilities collapse into certainties. Here's a twist for your sleepy mind. Even if you try to be sneaky, even if you set up a measuring device that doesn't directly disturb the particle, the interference still vanishes. The particle knows you're watching. Somehow the knowledge itself, your mere attempt at finding a path, forces the particle to pick one. Not both, not a wave, just one slit, one answer. This is the part where even seasoned physicists throw up their hands and go for a long walk, or a long drink, or both. You're now surrounded by glowing outlines of alternate paths, every possible route the particle could have taken. It's like a flowchart created by an anxious squirrel, branches within branches, each one ending in a soft dot on the far wall. But only when you stop trying to watch, when you leave the particle alone, does the full wave of possibilities play out. You realise with some unease that the universe seems to prefer being left alone to do its weird dance. But what is this interference pattern really? It's the result of a wave function, the math that describes all the possible states a particle could occupy. And those waves aren't physical waves like sound or water, they're probability waves, and when they interfere, it's not their physical paths overlapping, it's their likelihoods, their chances, their what-ifs. You sit down on a floating bench made of folded graph paper and rest your head in your hands. A screen materializes beside you, replaying the double slit experiment with different particles, electrons, protons, even entire molecules made of over 800 atoms. All of them behave the same, like waves, until you peak. Then snap, they're back to boring particles. And here's a particularly delicious slice of madness. There's something called a delayed choice version of this experiment. In this twist, you don't decide whether to measure the path until after the particle has passed through the slits, but before it hits the detector. And even then, your decision seems to reach back in time and change what the particle did earlier. Did it behave like a wave or a particle? Your choice appears to dictate that, even retroactively. Physicists still debate whether this implies time is an illusion, or if causality itself is just another nice idea we cling to for comfort. You walk now through a tunnel lined with holographic plaques. Each shows a scientist with increasingly tired expressions, Feynman, Bohr, Wheeler, all trying to explain the unexplainable. One plaque flickers with Feynman's voice. Nobody understands quantum mechanics. He said it cheerfully, like a man who's seen the abyss and brought back snacks. Let's toss in a quirky tidbit. In 2011, researchers in Vienna used fullerenes, giant soccer-ball-shaped molecules of carbon, to perform a version of the double-slit experiment. The molecules were enormous by quantum standards, yet they still produced an interference pattern. Reality held the door open for them, even when they practically needed name tags. You finally exit the tunnel back into the shimmering void. You glance behind at the double slits. They're still there, still daring you to look, or not look. You realise that every particle in the universe might be doing this dance right now, wavering between paths, collapsing into outcomes only when forced. Maybe you're doing it too. Maybe, in some cosmic sense, every choice you make is a slit, and you only know which path you took after it's too late to change. And maybe, just maybe, the version of you who chose differently is still walking through a different slit, leaving behind a different pattern. The room you enter next feels different, quieter, as if the universe itself is holding its breath. The walls curve inward, not with menace, but with a kind of delicate tension, like a soap bubble that might pop if you ask the wrong question. You step in slowly. There's a single chair in the middle pointed toward a screen. The moment you sit, it flickers on and there's you, in grainy black and white, frozen mid-gaze. You're being watched, and just like that, everything changes. You know this feeling. The shift in posture when someone's eyes are on you, the tightening of expression, the adjustment of tone. But in the quantum world, it's more than social anxiety. It's physics. The mere act of observing a system alters the system itself. You're not just watching, you're interfering, you're collapsing possibilities. And now the universe is staring back. This is the observer effect, a concept so central to quantum mechanics that it might as well be carved into the door of every laboratory. The idea is simple, terrifying, and deeply misunderstood. At the quantum level, you can't observe something without disturbing it. The act of measurement forces nature to choose. Before that, it's all shimmering maybes. Take your favourite particle, say an electron. Leave it alone and it exists in a wave-like haze of probability. Pin it down, measure its position, its spin, anything, and it instantaneously collapses into a single outcome. It's like trying to photograph a cloud and discovering that the act of snapping the picture turns it into a snowball. Historians still argue whether the observer effect is about consciousness or just interaction. Some interpretations insist that it's not you observing that changes the system, but the measuring device itself, the particle bumping into a photon or a sensor or a lab instrument. Others suggest something more radical, that awareness plays a role, that the presence of a conscious observer is what causes the wave function to collapse. You glance again at the screen. Your image is gone now, replaced by footage from a real experiment, a cloud chamber in a darkened lab. A stream of particles enters. Some leave trails, others don't. One of them seems to change direction just before it's observed. No visible cause, just a reaction to being watched. In this unsettling little world, attention is power. You walk forward and the walls dissolve, revealing a vast observatory made entirely of glass and gold thread. It floats in darkness, filled with floating orbs, tiny systems waiting to be observed. As you approach one, it hovers anxiously. You haven't measured it yet. It still exists in a quantum haze. You're tempted to leave it alone, let it stay undefined. But curiosity always wins. You reach out, and it pops into clarity. The haze is gone. One version becomes real. The others vanish like forgotten dreams. This raises a dangerous question. How much of the universe stays undefined until something or someone looks? There's a famous experiment that leans into this discomfort even harder. It's called the quantum eraser. In it, particles go through a double-slit setup and leave the usual interference pattern, unless you record which path they took. But here's the twist. If you erase that information after the fact, the interference comes back. It's like the universe forgives you for watching as long as you promise to forget. One version of this experiment even allows you to choose whether to keep or erase the path information after the particle has landed. And yet your decision seems to influence whether it behaved like a wave or a particle beforehand. Time, apparently, is not immune to shame. You step into a chamber lined with mirrors, all pointed inward. You see infinite versions of yourself, watching, measuring, guessing. And for the first time tonight, you wonder, is it possible to observe without interfering? Is there any way to just see without altering the outcome? So far, the answer is no. The observer effect is built into the very equations of quantum theory. And no matter how delicately we construct our experiments, no matter how indirect our measurements, there's always some disturbance, some echo of our intrusion. The universe doesn't offer silent witness, it reacts. Here's a quirky historical note to chew on. In 935, John von Neumann argued that no matter how many layers of measurement you add, sensor after sensor, machine after machine, eventually the wave function has to collapse somewhere. And since machines don't have awareness, he suggested the final step might require a conscious observer. That idea was later echoed by physicist Eugene Wigner, who even included his friend's mind in the experiment. Wigner's friend, it's called. And yes, it's exactly as awkward as it sounds. Imagine this. Your friend is in a lab observing a quantum system. To her, the wave function collapses when she sees the result. But to you, who hasn't looked in yet, both your friend and the result are still in superposition. So, who's right? Has the wave function collapsed or not? Is your friend both a witness and not a witness? It's the quantum version of peeking into someone else's dream and finding out it's yours too. Physicists still haven't settled the issue. Some say consciousness is key. Others insist the collapse happens at the point of entanglement or decoherence. A few sidestep the issue entirely and say, "Shut up and calculate." But the debate lingers. In science, nothing draws more suspicion than mystery tied to awareness. You walk back out into open space or the glass observatory behind you crumbles into stardust. A whisper floats past you. Are you watching or being watched? You look up. There's no one there. Or maybe everyone is. Maybe this whole place, this strange quantum landscape, is reacting to you. And maybe, just maybe, it was always waiting for someone to see it. You're still thinking about that last question, watching or being watched, when you walk straight into a wall. Not metaphorically, a very real, very cold-looking wall. You stagger back, rubbing your forehead. Okay, fair enough. Even in a quantum dreamscape, a wall is a wall, except this one isn't. You step forward again cautiously. You press your palm against the surface. It feels solid, dense, impenetrable, and then, without warning, your hand goes through it. No resistance, no sound, just a gentle shimmer, like air rearranging itself to let you pass. You flinch and yank your hand back. It's still there, whole, unburned, unscrambled. What just happened? Welcome to quantum tunneling, the phenomenon where particles do something they absolutely shouldn't. Break the rules. Not by force, but by sidestepping them altogether. Imagine you're a tiny ball trying to roll up a hill, but you don't have enough energy to reach the top. In classical physics, you'd roll back down, defeated. But in the quantum world, sometimes, improbably, you just appear on the other side of the hill. Not because you climbed it, not because someone pushed you, just because the laws of physics quietly looked away for a moment. And there you were. It sounds absurd, it is absurd, and yet it's happening all around you. The reason has everything to do with wave functions. Remember those hazy clouds of possibility we talked about? Well, they don't vanish immediately at the edges of barriers. Instead, they leak through. The probability of finding a particle on the other side isn't zero, it's just very small. But quantum mechanics doesn't care about your intuitions. If there's even a sliver of chance, the universe might just roll the dice and say, why not? You step forward, and your whole body passes through the wall. It feels like walking through a thick curtain made of static electricity and soft fog. On the other side, the air is cool and smells faintly like ozone and improbable decisions. You find yourself in a long corridor filled with translucent barriers. They flicker like holograms, shifting subtly every time you blink. You watch a stream of particles approaching one. Most bounce off, as expected, but a few, just a few, pass through, like VIP guests at a party you didn't even know was happening. They don't crash the barrier, they ghost through it, like secrets slipping between lines of code. Quantum tunneling isn't just a theoretical curiosity, it has practical consequences. The very process that powers the sun, nuclear fusion, depends on it. Inside the sun's core, hydrogen atoms are packed so tightly that statistically speaking, some of them tunnel through the repulsive electric barrier keeping them apart. When they do, they fuse, releasing the energy that warms your skin on a summer day. So yes, your tan exists because particles cheat. Historians still argue whether early physicists fully grasped what they were implying when they accepted tunneling into the math. George Gamow, one of the first to describe it, was actually trying to explain how radioactive particles escaped from atomic nuclei. The odds were astronomically low, but the math kept saying it happens, trust me. And we do. Your phone wouldn't work without it. Quantum tunneling is essential in modern electronics, particularly in semiconductors and devices like tunnel diodes and quantum dots. Even scanning tunneling microscopes, which let us see individual atoms, rely on electrons that refuse to stay where they're supposed to. You reach out toward one of the barriers and find a note pinned to it. It's handwritten, in looping cursive. What you call impossible, I call poorly defined. You chuckle. It's probably meant to be profound, but right now it mostly sounds like something you'd find on a mug at a gift shop run by Schrödinger. You walk further and arrive at something stranger, a vending machine. It's labelled classical options only. It has two buttons, Snack A and Snack B. You press one and a small orb appears. You press the other and a different orb materialises. Then you notice a third button, Tunneling Chance. You press it, and to your disbelief, both orbs appear simultaneously, having somehow bypassed the classical restrictions. This is tunneling on display, not breaking the rules, but finding the loopholes buried in the fine print. you keep moving. The corridor narrows into a tunnel of its own, curving downward, deeper into the quantum realm. Along the walls are snapshots of particles mid-tunnel. Some have warped wave functions that stretch from one side of a barrier to the other, like a tightrope walk made of uncertainty. Others leave no trace except where they reappear. And here's the quirky part. Tunneling can sometimes happen faster than the speed of light, or so it seems. It's not that information is travelling faster than it should, it's that particles act like they never spent any time in the barrier at all. This apparent instantaneous behaviour makes some physicists uncomfortable. Others just shrug and say, "It works, don't think about it too hard." Of course we do think about it, and some fringe researchers have proposed that tunnelling might one day enable things like ultra-fast travel, or even communication across impossible distances. But for now, the effect is too chaotic to harness on that scale. You can't predict which particle will tunnel or when. You can only calculate the odds and wait. You emerge at the end of the tunnel and find yourself back in open space, surrounded by constellations made of equations instead of stars. Each one glows softly with probability amplitudes, dancing in and out of focus. You realise something now. Tunnelling isn't just a quantum trick, it's a metaphor, maybe even a comfort. That even when the path looks blocked, even when the laws seem firm, sometimes, just sometimes, the universe lets something slip through. Maybe you will too. It feels like space now, wide, cold, still, but not the vacuum you've read about in textbooks. This isn't a clean, empty void. It's alive. It's twitching. It buzzes faintly under your feet, under your breath, under the layer of calm you've been clinging to since this quantum journey began. You expected silence here, nothingness, peace. But instead, you're standing in a place filled with noise you can't hear, particles you can't see, and fields that seem to ripple just because you are. This is the quantum vacuum, and it is not empty. If you believe the classical version of nothingness, this part will hurt your feelings, because in quantum physics, even a vacuum, a region stripped of all matter, all particles, all light, isn't truly devoid of activity. Even when you've turned off every source, cooled everything to absolute zero, and cleared the board, there's still something. A seething, shifting background hum. The vacuum, it turns out, is a liar. You begin walking and the path is marked not with signs but with subtle blips, flashes of energy, as if something just appeared and vanished before you could focus on it. These are virtual particles, the tricksters of the quantum world. They pop into existence and disappear again almost instantly, borrowing energy from the vacuum, performing a brief pirouette, and vanishing before the cosmic ledger notices. You reach out to one, too slow, but another one flits by your shoulder like a firefly made of question marks. It has no mass, no charge, no history. It never existed in a classical sense, and yet it left an imprint. That flicker was real. Ish. Historians still argue whether virtual particles should even be called particles. They are not directly observable. They don't leave tracks, but their effects are measurable. They're the reason atoms don't collapse, the reason radioactive decay happens, the reason the universe, despite its best efforts, refuses to be still. You stop beside a strange machine, half telescope, half tuning fork. It's aimed at nothing, but its sensors are twitching, showing tiny jolts of energy where none should exist. Welcome to zero-point energy, the lowest possible energy that a quantum system can have, even when everything else is removed. It's not just a leftover, it's a feature. The universe's resting state is not zero, it's jittery. This background buzz affects everything. It creates a subtle pressure on objects in a vacuum, a phenomenon known as the Casimir effect. If you place two metal plates extremely close together in empty space, they'll attract each other, not because of any visible force, but because virtual particles between the plates are restricted, while the ones outside aren't. The imbalance generates a tiny push pulling the plates together. Space itself conspires to create motion. You drift closer to a pair of plates now, watching them edge imperceptibly inward, nudged by invisible fluctuations. The motion is so slight it would take a lab of mind-blowingly precise instruments to detect. But it's real. In fact, it was measured in 1948 by Dutch physicist Hendrik Casimir, who was just trying to understand quantum electrodynamics better and accidentally revealed that empty spit has opinions. You pass a table labelled vacuum tricks, where other effects lie scattered, like tools in a magician's workshop. There's vacuum polarization, where the electric field around a charged particle gets distorted by the vacuum's own ephemeral crowd of virtual particles. There's Lamb shift, yes, like the meat, an observed shift in energy levels of hydrogen atoms caused by the quantum vacuum poking at them gently but persistently. It starts to feel less like a void and more like a restless playground. One with no children, no swings, but plenty of mysterious forces whispering through unseen seesaws. You walk further and notice something big, really big, looming ahead. A massive black sphere. It pulses slightly like a sleeping eye. You realise what it is, a black hole, or rather, a simplified version of one. And just outside the event horizon, flickering particles appear. One pair, then another. Each pair consists of a particle and an antiparticle, born from the vacuum, and in most cases, they annihilate each other and vanish again. But near a black hole's edge, sometimes one falls in, the other escapes. That's Hawking radiation. Stephen Hawking proposed that black holes aren't perfectly sealed. They can slowly evaporate, leaking energy thanks to these quantum fluctuations at the event horizon. Not because anything escapes the black hole itself, but because the vacuum is never truly quiet. The particles it generates keep messing with the boundaries. A fringe scientist once called the vacuum the universe's backstage crew, invisible, tireless, always working. They're not wrong. You can't see these effects in daily life, but they're woven into the fabric of every force you take for granted. Magnetism, light, atomic structure, all of it rests on the not emptiness of the void. And if that isn't enough to scramble your sense of comfort, here's a kicker. This vacuum energy might be linked to the expansion of the universe itself. The mysterious force known as dark energy, pushing galaxies apart at increasing speed, could be a result of vacuum fluctuations, or something deeper, something we still don't understand. You lie down for a moment, flat on your back in this imaginary quantum plane, trying to imagine a world where nothing really meant nothing. No fields, no energy, no fluctuations, just total stillness. You can't do it. Your brain won't let you. And maybe that's the point. The quantum vacuum hums quietly beneath you. It's not loud, not violent, just ever-present. Like a low-frequency promise that something is always happening, even when you think it's not. And you realise, true silence doesn't exist. Not in this universe. There's something strange about the light now. It doesn't move normally. It doesn't flicker or cast shadows like it should. Instead, it seems to split, doubling back on itself, twisting into shapes you can't follow, like watching reflections ripple across a lake that isn't there. You try to focus on one ray, and in doing so you feel a headache that doesn't belong to your body. It belongs to every version of you that could be standing here. Because you're not just you anymore. You're all the possible yous. Welcome to the many worlds interpretation. This is the part where reality stops pretending to be polite. No more collapsing wave functions, no more convenient measurement-based decisions. Instead, the universe branches, again and again and again. Every quantum event, every choice, every outcome that could happen does happen. Somewhere. In some version of the universe. And every time it happens, a new timeline splits off, taking its own you with it. You're in a hallway now, lined with mirrors, but the reflections don't match. Each one shows a different version of you. One wearing a hat you don't own, one smiling when you're not, one mid-sentence saying words you never said. These aren't reflections, they're neighbouring worlds, parallel universes, realities born from divergence. It sounds like science fiction, but it's a serious contender in quantum theory. Proposed by Hugh Everett III in Mod 57, the many worlds interpretation was his attempt to get rid of that pesky wave function collapse altogether. Instead of the wave function choosing one outcome when observed, he argued, it keeps all of them. Measurement doesn't destroy superposition, it distributes it. Every outcome gets its own world. You open a door just to see, behind it, you, reading a book. You recognise the title. It was a choice you didn't make weeks ago. You closed the tab, you moved on, but this version of you didn't. He read the book. He's different now, wiser maybe, or just more confused. In another room, you see a version of yourself who never took that detour, never opened this quantum rabbit hole. He looks calmer, slightly bored. You shut that door quickly. The many worlds idea isn't about imaginary hypotheticals, it's a serious response to the messiness of measurement. If the wave function never collapses, then it has to go somewhere. So it does, into an ever-branching tree of realities. At every interaction, every fork, the world splits, not with a bang, not with a shimmer, but with a quiet shift you'll never feel. Historians still argue whether Everett's proposal was born from a deep intuition or a frustration with the Copenhagen camp. At the time, his ideas were dismissed. Even his mentor, John Wheeler, didn't fully buy in. But as quantum theory has matured, and as experiments have continued to show just how weird and stable superpositions are, Everett's once heretical idea has become more mainstream. You walk deeper into the corridor of selves, and with every step the air feels heavier, not because it's oppressive, but because you're aware of every version of your body walking other hallways, in other realities. It's like catching glimpses of your own footprints on a beach you've never visited. There's a control panel ahead. It doesn't let you jump worlds, no shortcuts, but it shows probabilities. Version 3421 chose tea instead of coffee, probability 48.2%. Version 9782 never left that toxic relationship, probability 13.5%. It's sobering. Each decision you agonized over, it exists in full somewhere else, lived out, finalized, still unfolding. A quirky side note. Many Worlds has found unexpected fans outside of physics, philosophers, sci-fi writers, even investors. There's a story about a hedge fund manager who once joked that he didn't worry about risk because in at least one world, he always wins. That's not advice. That's quantum gambling with emotional baggage. Back to the science. One objection to many worlds is that if all outcomes happen, how do we make predictions? If there's a world for every roll of the dice, what does probability even mean anymore? Some argue that we still experience relative probabilities, that the worlds where less likely events happen are just vastly fewer in number, and thus we're less likely to find ourselves in them. Others insist the concept breaks down entirely, but math still works. The predictions of quantum mechanics remain rock solid, regardless of whether there's one world or infinite. You lean on a railing and look out over what seems to be a vast forest of realities, each path branching and twisting into fractal spirals of cause and effect. Somewhere down there is a version of you who turned left instead of right, one who never watched that documentary, one who kissed them back, one who never said yes, or said yes too soon. It's humbling, not because you're insignificant, but because every choice you've ever made has siblings. Not ghosts, not illusions, fully fleshed, logically inevitable branches of the same tree. If that makes you feel better about the mistakes, good. If it makes you panic about the infinite scale of things, also fair. And here's a fun, slightly horrifying thought. In the many worlds view, death isn't an end. In at least some universes, your heart keeps beating. Your cancer never started. The bus missed you by inches. You keep going somewhere. Not because you're immortal, but because there are infinite versions of you. Statistically, some just keep surviving. It's a fringe idea with a name, quantum immortality. Don't get attached to it, but it's there. You finally exit the Hall of Mirrors and step onto a small bridge made of light. It trembles slightly beneath your feet. For a moment, you think about how many yous have walked this bridge, how many others never found it. You wonder who you're leaving behind each time you make a decision. You wonder who's leaving you. Then you move forward, 1 foot, 1 world at a time. You enter a room that looks like a server farm, but designed by someone who builds dreams for a living. Cables flow like rivers, blinking lights pulse in sync with your heartbeat, and in the center of it all stands a machine that hums softly, as if it's thinking in ways you can't quite follow. You take a few hesitant steps toward it, expecting the usual digital order. Instead, what you find is logic turned sideways, classical rules bent into Mobius strips. This is quantum computing, and it does not care about your binary expectations. Classical computers are neat creatures, ones and zeros, on or off. They do math by flipping switches at ridiculous speeds, chaining together tiny truths until something useful comes out, like a search result, a song, or a gentle reminder that you've once again forgotten your password. But quantum computers? They play an entirely different game, one where the pieces exist in multiple states, entangle with each other, and behave like they're trying to win a logic puzzle with interpretive dance. You watch as a qubit hovers before you, qubit short for quantum bit, the basic unit of information in a quantum computer. It spins gently, in a kind of shimmering indecision. It's not a 1, it's not a 0, it's both, in superposition, and that's its power. It doesn't have to choose yet. Another qubit floats nearby, and then another. When they link, the air around them thickens with possibility. Because once entangled, these qubits don't just compute in isolation. They compute together, their states dependent on one another, dancing through solutions in a way that would melt a classical processor's metaphorical brain. You're now standing inside the quantum processor itself. It's not made of silicon. It looks more like a chandelier of frozen light, cooled to near absolute zero. Why so cold? Because quantum states are fragile. Any heat, any noise, even the tiniest vibration can cause decoherence, the collapse of the qubit state into something ordinary and, frankly, boring. Historians still argue whether quantum computing was inevitable or just a beautifully lucky consequence of decades of theoretical frustration. The concept was formally introduced in the 1980s by physicists like Richard Feynman and David Deutsch. Feynman was frustrated that classical computers couldn't simulate quantum systems without a ridiculous amount of effort, so he proposed something radical. What if we built computers that ran on quantum rules instead of fighting them? You peer into one of the logic gates now, watching as 3 qubits flow through. In a classical computer, this would be a simple operation, maybe a NOT gate, maybe an AND. In a quantum system, it's a unitary transformation, a twist through an abstract mathematical space that feels less like arithmetic and more like a very precise form of sorcery. The beauty and the curse of quantum computing is that it doesn't give you every answer. It gives you the right answer, if you know how to ask the question properly. You set up your quantum Sutton system, let it evolve through its mind-bending math, and then, crucially, you measure. And when you do, just like always, the wave function collapses. You get one result. But behind that single answer is a whole dimension of probability, an entire forest of paths that help shape what you see. You pass a screen labelled Shor's algorithm, now in 3 dimensions. It plays an animation of prime factorization, splitting large numbers into their prime components. This task would take a classical computer centuries for a really big number. A quantum computer? Just a few moments, at least in theory. Shor's algorithm, developed in 1994, remains one of the most famous examples of quantum advantage. If you want to terrify cybersecurity professionals, just whisper "Shor" at a conference. There's another screen nearby, this one labelled Grover's algorithm, now with 30% more search. It shows a spinning list of unsorted items, names, passwords, locker combinations. Grover's algorithm allows quantum systems to search through unstructured data faster than classical systems ever could. Not instantaneously, mind you, but significantly faster. Enough to change how we think about optimization, cryptography, and maybe even artificial intelligence. A quirky bit of trivia for your collection. Quantum computers don't just live in theory anymore. Real ones exist, sort of. Companies like IBM, Google, and D-Wave have built early-stage machines with tens to hundreds of qubits. They're delicate, noisy, often require complex error correction, and take up entire rooms, but they're real, and they're improving. You turn now and see a wall labelled Quantum Error Correction. It's covered in warning labels and panicked equations. Qubits, while powerful, are fragile little creatures. They decohere easily. They misbehave, so scientists have created redundancy systems, like building quantum triplets and using clever math to detect when one falls out of line. It's not glamorous, but without it, your elegant quantum logic dissolves into quantum nonsense. You stand beneath a dome now, and it projects a simulation above your head. You watch as a complex quantum computation unfolds, thousands of entangled qubits mapping out a probability landscape that looks more like a topographical map of anxiety than anything else. But at the end of it, a single bright point. The answer. Not just any answer, but the best one, from a sea of near misses. And you realise quantum computing isn't faster because it cheats. It's faster because it calculates in parallel, not in space, but in possibility. It's like asking every version of you across infinite universes to work on the problem at once and then agreeing on a winner. The lights dim and you exit through a narrow hallway of questions. Can it break encryption? Will it power AI? Is it already being used secretly? The answers hover somewhere between hype and hardware. You walk away from the machine brain buzzing, not because you understand it fully, you don't, no one does, but because you felt it, the shift from classical certainty to quantum maybe. The realization that logic, when twisted just right, can open doors you never knew were locked. And in the distance, the hum of a qubit still spinning reminds you. Possibility is not just a feature, it's the system. The next chamber greets you with an odd sensation, not exactly disorientation, but a gentle betrayal of your expectations. Everything here feels normal. The floor is firm, the lights cast clean, reliable shadows. You look down at your hands, expecting them to shimmer or blur, but they hold steady. You take a cautious step forward. Nothing tunnels, nothing flickers. For the first time in what feels like an eternity, physics seems to behave, which is suspicious. You've crossed a threshold now, and this space, the place where quantum becomes classical, isn't defined by a wall or a switch. It's defined by a process, a strange, slow loss of weirdness. This is decoherence, the great untangler. The reason your coffee doesn't quantum leap out of the cup, the reason you don't walk through walls, the reason the moon doesn't disappear when you stop looking. Decoherence is the invisible referee between the quantum world and our everyday one. It happens when a quantum system becomes entangled with its environment, air molecules, radiation, a curious lab assistant, and in doing so loses its delicate superposition. Not because it wants to, not because it fails, but because reality is noisy and quantum weirdness can't survive in a crowd. You pass a diagram etched into glass. It shows a lonely qubit, vibrating in its weird little space, both 0 and 1. But then, a line connects it to an environment, heat, photons, other particles, and suddenly its quantum state collapses. Not from measurement, but from interaction, from exposure. Decoherence doesn't kill the superposition, it drowns it in entropy. Historians still argue whether decoherence counts as a true explanation for the measurement problem or merely a description of how quantum weirdness fades. Some physicists believe it's the key to understanding the classical world. Others say it just pushes the mystery one level deeper, into murkier math. You step through a museum-style exhibit titled "Why You Seem Normal." Each display case holds a tiny quantum system, slowly losing coherence as it interacts with the world. An atom becomes a molecule becomes a vibrating string of possibilities, then a blurry shadow, then poof, something familiar, something measurable, something boring. You touch the glass, it's cold. There's a video looping nearby showing an experiment with fullerene molecules, big complex things that still display quantum interference. But only under extremely controlled conditions. As soon as they warm up or bump into air molecules, their coherence unravels, like a song drowned out by static. Decoherence, in a sense, is why you don't live in a superposition of leaving your keys on the counter and the fridge. It's why your cat isn't both under the bed and on top of the cabinet. The quantum world doesn't vanish, it just hides behind noise. Its delicate order gets swallowed by the thermodynamic messiness of life. You walk into a quiet room now, where your footsteps echo slightly. On one wall is a series of clocks, each ticking slightly out of sync. They're labelled electron, carbon atom, virus, grain of sand, you. As the scale increases, the ability to remain in superposition drops dramatically. The bigger the object, the more it interacts with its surroundings. And interaction means decoherence. You realise the transition from quantum to classical isn't abrupt, it's gradual, a slope, not a cliff. And at the top, you're still partly quantum. Your neurons, your molecules, they hum with potential. But the orchestra of interactions, heat, gravity, consciousness, pulls them into chorus, into normalcy. But here's the strange part. Decoherence doesn't explain why you see just one outcome. It explains why interference disappears, why superpositions become unobservable. But it doesn't answer the fundamental question: why do we see a definite result? Why does your brain perceive this version and not the others? That's where interpretation still wrestles with uncertainty. Some schools argue that decoherence is all we need, that once a quantum system gets tangled with enough of its surroundings, the illusion of classical reality emerges naturally. Others argue that this just kicks the quantum can down the road. If the wave function keeps evolving smoothly, why should your conscious experience lock into a single thread? You enter a side room labelled macroscopic superpositions, the forbidden zone. Inside are strange, preserved thought experiments. Schrödinger's cat, of course, pacing quietly inside a glass cube. Next to it, a hypothetical human brain in superposition flickering between possible thoughts. It's uncomfortable to look at. You sense your mind rejecting it like a bad taste. And yet, some researchers have tried. In 2020, a group attempted to entangle a small drum, microscopic but still massive compared to an electron, with a quantum state. They saw hints of interference, hints that decoherence hadn't entirely won, but it's a war of attrition. The larger the object, the faster it decoheres. Still, the frontier moves, bit by bit, system by system. You pause by a sculpture titled Collapse by Consensus. It shows a quantum state surrounded by measuring devices, all shouting at once. The state collapses not because of any one observation, but because the combined pressure of the environment demands a decision. It's funny, in a tragic way. Quantum systems are like introverts. They can only be themselves when left alone. You take one more step and the room begins to dissolve. The crisp lines fade, the colours soften. You're no longer in a defined space, but in something liminal. A blur between what is and what might have been. Decoherence hasn't reached this places yet. And that's when it hits you. The reason you don't experience quantum weirdness in everyday life isn't because it isn't there. It's because the world around you, the warmth of the air, the photons bouncing off your skin, the ticking of time itself, insists on choosing a story. You are the result of decoherence. Your memories, your identity, your sense of linear time, all of it shaped by quantum systems too large and too tangled to stay weird. Not because they can't, but because reality is loud, and quantum coherence is easily drowned. Still, deep down, beneath your cells, beneath your thoughts, a sliver of that weirdness lingers, waiting, not dead, just too quiet to hear. You find yourself descending now, no stairs, no gravity, just a slow pull downward as if the quantum realm has decided to lower you gently into something more obscure. The air feels different here, more contemplative, less spark, more shadow. You land on a soft surface that shifts beneath your feet like velvet fog. Around you the walls stretch and sway, not like solid structures, but like ideas in motion. You've arrived at a place few visit without an agenda, the land of alternative interpretations. Tonight's candidate? Bohmian mechanics. Of all the ways physicists have tried to explain quantum behaviour, Bohmian mechanics is among the most peculiar and the most persistent. Here, particles are real, definite, and always have exact positions. There's no fuzzy maybe cloud of probability, no undecided paths. In this version of quantum theory, particles have clear trajectories, but those paths are steered by something invisible, a pilot wave. You walk alongside a glowing path now, and you can see the particle. It's small, sharp, and stubbornly local. But its movement isn't random. It's guided by a wave function that stretches across space like an invisible wind, nudging it left, right, forward. Not pushing, guiding, whispering directions. You realise you're not watching a guessing game. You're watching choreography. Bohmian mechanics, sometimes called the pilot wave theory, originated from a 1907 paper by Louis de Broglie, though it was David Bohm who truly fleshed it out decades later. At a time when the Copenhagen interpretation dominated quantum discourse, Bohm dared to say, what if we just stopped collapsing the wave function? Instead, he proposed a model where the wave function exists alongside the particle, always present, always directing, like a GPS with no voice, just a perfectly silent plan. Historians still argue whether Bohm's approach was a brilliant act of realism or an unnecessary complication. Critics say it adds more baggage, hidden variables, non-locality, an extra layer of metaphysics. Supporters counter that it makes quantum mechanics deterministic again, predictable, palatable, less like a fever dream, more like a strange but comprehensible machine. You now find yourself in a room labelled real particles, imaginary roads. It's a kinetic model of Bohmian mechanics. Tiny spheres move through space, leaving shimmering trails behind them. Their paths seem to curve without contact, as if they're following invisible lines drawn in a fifth dimension. You notice one veering toward a slit in a wall, like in the double slit experiment, and you brace yourself for the usual nonsense. But it doesn't split. It goes through one slit, just one, and yet, on the screen behind it you still see the interference pattern. You blink, the math still works. Bohm's model gives the same predictions as standard quantum mechanics, the same wave behaviours, the same strange results, but underneath it insists on a hidden realism. a belief that things really do have positions and velocities even when you're not looking. Of course, it comes with a trade-off: non-locality. In Bohm's model, changes in the pilot wave can instantaneously affect a particle, no matter how far apart they are. Sound familiar? It echoes quantum entanglement, but here it's built into the foundation. There's no dodging it, no workaround. The universe is quietly wired together in a way we can't see or use, but which Bohm treated as fundamental. You wander through an archive of diagrams, each one an attempt to visualize how pilot waves guide particles through complex environments. One shows a labyrinth, the particle finding its way not by bouncing off walls, but by following contours of an abstract wave. It looks like intuition coded into physics, like a marble rolling downhill along invisible terrain. A projector flickers to life on the far wall, showing an experiment that inspired Bohm's thinking, the oil drop walkers. In this tabletop demonstration, droplets of oil bounce on a vibrating fluid surface, creating waves that then guide the droplet's motion. The result? A seemingly classical particle exhibiting quantum-like behaviours, tunneling, orbit quantization, even double-slit interference. The analogy isn't perfect, but it's eerily close. A particle guided by something deeper. Sound familiar? A small sign nearby reads, "The map is not the territory, but the map might be hiding in the wave." You smile. In Bohm's view, the quantum world isn't random. It just appears that way because we're missing information. The wave function knows more than we do. It guides every particle with perfect awareness of the whole system. A kind of holistic determinism, not mystical but deeply connected. Some even say spiritual, though Bohm himself warned against confusing physics with philosophy. You pause in a side alcove labelled Philosopher's Corner. There's a dusty chair, a warm lamp, and a quote engraved into the wall: "Wholeness in the implicate order." That's the title of one of Bohm's later works, in which he explored how particles and waves might just be surface phenomena, ripples in a deeper implicate structure, a kind of universal code from which reality unfolds. Fringe, maybe, but also oddly poetic. A quirky note for your dream journal. David Bohm once had long conversations with the Dalai Lama about the nature of reality. They bonded over the idea that the world might not be composed of things, but of relationships, patterns, connections. Bohm didn't just believe in pilot waves, he believed the universe itself was a dialogue. As the light dims, you return to the main path and a new sign welcomes you. Back to collapse, or not. You understand now why Bohmian mechanics isn't universally accepted. It solves some mysteries, but raises new ones. It explains the how, but dodges the why. It's elegant, yes, but also lonely. There's no measurement problem because there's no collapse. Just particles quietly following waves you'll never fully know. You take one last look at the trail behind you. It's faint, glowing softly with the certainty Bohm tried to offer. A world not of maybes, but of hidden truths, the kind you can't see but which carry you anyway. You close your eyes and feel yourself drifting upward again. You rise gently into the next chamber, carried not by momentum but by a kind of reluctant curiosity. The feeling you get when you're about to reread a chapter you didn't fully understand the first time. The air here is colder, not in temperature but in tone. The walls are simple, unadorned, a stark white emptiness, like the inside of a laboratory someone just vacuumed of mystery. There's no dramatic shimmer, no swirling equations, no entangled sculptures, just a chalkboard, and written on it in precise block letters, Copenhagen. Interpretation: shut up and calculate. You smile but not warmly. This, right here, is the old-school heavyweight of quantum theory, the mainstream model, the official narrative on your university exams, developed in the 1920s by a group of physicists centred around Niels Bohr in, you guessed it, Copenhagen. This interpretation has long reigned supreme not because it's beloved, but because it works. It doesn't coddle, it doesn't speculate, it just delivers the right answers, and then tells you to stop asking annoying questions about what's really going on underneath. At its core, the Copenhagen interpretation says this: the wave function contains all possible outcomes of a quantum system. But when you measure it, when you look, you get just one. Why? Because the act of observation causes the wave function to collapse into a single definite state. Before measurement, everything's in superposition. Afterward, one thing is real. period. You turn away from the chalkboard and find a glass cube in the middle of the room. Inside it, a tiny particle, vibrating with uncertainty. Next to it, a button labelled measure. You press it. Instantly, the particle snaps into position. One outcome. The others? Gone. Not hidden. Not moved to other worlds, just erased. The Copenhagen model says, don't worry about where they went. They're not part of your reality anymore. You shift uncomfortably. The appeal of this interpretation lies in its brutal practicality. It doesn't concern itself with what's really happening in the quantum world. It just gives you tools to predict what you'll see. It's the physics equivalent of plugging in your headphones, doing your work, and refusing to engage with the chaos around you. Historians still argue whether Niels Bohr himself even intended this interpretation to be final. His writings are notoriously vague, philosophical, poetic even. He spoke in riddles about complementarity, the idea that particles are both waves and not waves, depending on how you look. He insisted that quantum phenomena don't exist independently of observation, but he danced carefully around what that meant for reality itself. The physicist Wolfgang Pauli once said, with barely concealed sarcasm, that Bohr's explanations were like an atmosphere you could breathe but not describe. Einstein was less charitable. He famously hated the Copenhagen interpretation, deriding it with his "God does not play dice" line. Bohr reportedly responded, "Stop telling God what to do." It was petty, brilliant, and very, very quantum. You enter a corridor labelled conceptual landmines, and it's littered with philosophical tripwires. One plaque reads, "What counts as a measurement?" Another, "Does consciousness collapse the wave function?" And a third, slightly tilted, "Where does the boundary lie between the quantum and the classical?" The Copenhagen interpretation shrugs at all of them, not because it has answers, but because it doesn't care. This might be the only interpretation that admits it doesn't know what reality is, it just tells you what to expect. And for a long time that was enough. It's like a GPS that works perfectly but refuses to explain how satellites function. You're still getting where you need to go. You pass by a small theatre playing a grainy reenactment of the early debates. Bohr and Einstein pacing across a chalkboard battlefield. Einstein proposing thought experiments, trying to expose the gaps. Bohr countering with paradoxes of his own. The battles were elegant, intense, and unresolved. Einstein wanted a clear picture of reality. Bohr was content with probabilities. A screen nearby shows a timeline. For decades, the Copenhagen view dominated. It was taught, memorized, and rarely questioned outside a few philosophical circles. It helped build the foundations of quantum chemistry, atomic clocks, lasers, even the semiconductor revolution. It was the workhorse of physics, not flashy, not warm, but loyal. But here's the tension: it's not satisfying, it never has been. A quirky anecdote floats into view, a quote from physicist Asher Perez. "Quantum mechanics does not describe reality, it describes our knowledge of reality." That single sentence summarizes the Copenhagen ethos. It's not about the world out there, it's about your interaction with it, what you can measure, what you can predict. Anything beyond that? Not part of the deal. You reach a terminal where you're asked to run a simulation. A quantum particle, a detector, and a human observer. You run the scenario, the detector records the particle's position, the data is printed, and that's it. Nothing collapses until a result is observed. But when? When the detector clicks? When the result is read? When someone thinks about it? The screen fades to black. The answer remains a shrug. And this is what makes the Copenhagen interpretation maddening. It's like being given a magic trick with no explanation. You can reproduce it perfectly, again and again, but ask how it works, and the magician just smiles and says, "That's not your job." You sit now in a chair beneath a slow-turning mobile of atoms and waveforms. You realise that in the Copenhagen world, you live inside a map, not the territory. Your instruments, your eyes, your thoughts, they don't penetrate quantum reality. They create it, or at least they carve one version out of the haze. It's uncomfortable, but functional, and as your eyes grow heavy, you realise there's something strangely comforting about that. Like the world might be unknowable in its details, but predictable in its patterns. The universe doesn't offer meaning, only measurement. Not stories, but statistics. The lights dim further now, softening to an almost imperceptible glow. The buzzing of ideas fades to a distant hum. You lie back, not to reject the mystery, but to rest inside it. Reality, at least for tonight, can collapse on its own. The lights return gradually, as if someone has opened the curtains on a slow sunrise. You find yourself walking through a corridor that looks suspiciously organic, ribbed walls like muscle fibre, soft ambient pulses like distant heartbeats. You run your fingers along the edge of the path and it's warm, alive maybe. Everything feels a bit closer to home now, a little more biological, and that's because it is. You've entered your own body. Welcome to quantum biology. This is the field where things get weird in a new way. Because for decades, scientists assumed the quantum realm didn't extend very far into the messy, noisy world of living things. Quantum phenomena were thought to be too delicate, too fragile to survive inside warm, wet cells. Decoherence would wipe out superpositions long before anything useful could happen. Life, after all, is chaotic, and quantum weirdness, as we've seen, is a bit of a diva. And yet here you are, walking through the inner landscape of life itself, and discovering that quantum effects may not just exist here, they may be essential. You step into the first chamber, and it smells like sunlight and sugar. Welcome to photosynthesis, the process by which plants, algae, and certain bacteria turn light into chemical energy. It's an ancient and crucial mechanism, one of life's foundational tricks. For years, it was explained in purely classical terms: light hits chlorophyll, electrons jump, energy transfers boom, sugar. But in the early 2000s, researchers began to notice something strange. Energy didn't just transfer, it travelled with surprising efficiency, as though it knew the best path in advance. Classical physics couldn't quite explain it, and so quantum coherence entered the chat. Inside the light-harvesting complexes of plants, when a photon excites an electron, that energy doesn't just bounce randomly around until it finds the reaction centre. It spreads out like a wave, exploring all possible paths simultaneously, a little quantum superposition tour, if you will, and the energy arrives almost perfectly, like it took the quantum equivalent of a shortcut. Historians still argue whether this coherence lasts long enough to make a real difference, or whether the biological system simply evolved to mimic quantum efficiency. But the evidence keeps stacking up. Even at room temperature, even in biological goo, the math of quantum transport seems to apply. You step through a glowing membrane into a new room filled with feathers, wings, and the shimmer of unseen maps. This is where quantum biology takes flight, literally, because birds, it seems, might navigate using quantum entanglement. Specifically, migratory birds like robins appear to possess a protein called cryptochrome, which may allow them to see Earth's magnetic field, not with iron filings or compasses, but through quantum spin states. Inside cryptochrome, when a photon strikes the molecule, it creates a pair of entangled electrons. These electron spins are sensitive to magnetic fields, and the angle between them affects how the bird perceives light. So the bird is not detecting magnetism directly, it's detecting changes in the chemical reactions caused by entangled particles. That's right, birds might be using quantum entanglement to see geography. You blink and imagine trying to navigate a city using mood shifts caused by subatomic spin flips. Suddenly, Google Maps feels outdated. A quirky fun fact for your mental journal. In 2011, physicists found that European robins could be disoriented by weak radio frequency fields, not strong enough to affect classical magnetism, but enough to interfere with delicate quantum spin states. Translation: mess with the bird's quantum entanglement and it flies in circles. And birds aren't alone in their quantum stunts. Step forward into the next chamber. It pulses with rhythm like a tiny drum. You've entered the realm of enzymes. These microscopic machines speed up chemical reactions by insane factors, sometimes by trillions. And part of their power, it seems, may come from quantum tunneling. In some enzymatic reactions, instead of jumping over energy barriers, particles, particularly protons, simply tunnel through them. It's faster, cleaner, and more efficient. The enzyme folds just right, the potential barrier narrows, and the proton appears on the other side like it was never confined in the first place. Like a seasoned bank robber that walks through vault walls without leaving a trace. You realise now, quantum effects aren't limited to rare special occasions. They're built into the architecture of life. Evolution didn't skip the quantum layer, it co-opted it. The path ahead takes a darker tone, dimmed and throbbing softly. This is the room of smell, of all things. Olfaction, the overlooked sense, is also under quantum review. Traditional models suggested that smell came from the shape of molecules fitting into receptors, like keys into locks. But some experiments suggest that scent might also depend on the vibrational frequency of molecules, and that those vibrations might be detected via quantum tunneling, meaning your nose might be doing tiny quantum calculations every time you walk past a bakery. You shake your head. It's a lot to take in. Smell, vision, memory, direction, all potentially enhanced or even powered by quantum effects. This isn't about adding sci-fi flavour to biology. It's about accepting that the boundaries between disciplines aren't as solid as they pretend to be. And here's the twist that scientists are only beginning to poke at. What if the brain, the thing thinking these thoughts, is itself quantum in some way? That question divides the room. Some claim that the brain's heat and messiness rule out any sustained quantum effects. Others point to recent theories, like orchestrated objective reduction, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, which suggest that microtubules inside neurons might support quantum coherence. It's fringe, it's controversial, but it's not off the table. You sit for a moment on a bench that appears to be made of folded DNA. Around you, a holographic projection plays out simulations of photosynthesis, bird navigation, enzyme action, all woven with a subtle thread of quantum logic. The math is everywhere, not dominating, not screaming, just present, like a quiet conductor guiding the orchestra of life. You lean back and let the hum of it all wash over you, because whether or not your thoughts are quantum, the truth remains, life didn't emerge in spite of quantum physics. It emerged through it. The transition is nearly imperceptible, like slipping into a dream from within another dream. The biological warmth fades. The heartbeat hum of quantum life recedes, replaced by something colder, stranger, and far more difficult to hold in your head. You're not in a room anymore, you're in a moment. Or perhaps a smear of them, layered like fogged glass, each one whispering, now? Or maybe, then? You've arrived in quantum time. In the classical world, time is a straight line. It ticks forward, second by second, never bending, never backtracking, cause precedes effect, and the past is sealed while the future stretches into blank possibility. But down here, in the microscopic jungle of the quantum world, time isn't quite so loyal to your expectations. It stutters, it loops, it delays its own decisions, and sometimes in ways we're still struggling to grasp, it might not even be real at all. You stand at the edge of a slow river, not of water, but of events. Each ripple is a quantum interaction. Most flow downstream as you'd expect, but every so often one seems to double back. A photon glances over its shoulder, an electron hesitates. You reach out to touch the flow, and in doing so, the ripples rearrange. They always do when someone's watching. One of the most unsettling features of quantum physics is how it plays with temporal order. The clearest example, the delayed choice experiment, first imagined by John Archibald Wheeler. You watch as it plays out in front of you now, projected on a translucent wall of light. A photon approaches a beam splitter, essentially a fork in the road. It could take one path or another, or both. If you measure it before the split, you find it behaving like a particle. If you wait until after the photon has already travelled, and then make your decision about what kind of measurement to perform, it still reacts accordingly, as if your future choice has influenced its past behaviour. Historians still argue whether this means causality breaks down at the quantum level, or if we're just misunderstanding what time really is in this domain. Wheeler himself liked to hint at cosmic scale consequences, suggesting that choices made in the present could help shape the universe's past, not because we're magic, but because the fabric of time is more negotiable than we'd care to admit. You move now through a hallway of ticking clocks. Each one is melting, dripping seconds like soft candle wax. Some tick forward, some tick backward. Others seem to spin in place as if waiting for permission to proceed. This isn't art, this is an experimental exhibit, a visualization of quantum time symmetry. You see, most of the fundamental equations of quantum mechanics are time reversible. If you swapped t for et, the math would still work. In theory, the past and future are on equal footing. The only thing forcing time to move forward is something called entropy, a measure of disorder that tends to increase in closed systems. But quantum systems aren't always so cooperative. Sometimes their internal clocks run differently. You sit in front of a screen showing the quantum switch experiment, conducted in real labs with real photons. In this setup, the order of events isn't fixed. Whether A happens before B or B before A is determined only when you measure the outcome. Until then, both sequences exist simultaneously in superposition. Cause and effect take turns being each other. You raise your eyebrows, so do several physicists on the playback footage. Here's a quirky tidbit to sweeten the paradox. Quantum mechanics allows for something called indefinite causal order. That means that in certain setups, it's not just unknown which thing happens first, it's undefined. There is no true sequence until the system collapses. Time isn't just fuzzy, it's conditional. This leads you into a deeper, quieter chamber. The walls are lined with floating orbs, each containing a tiny version of the universe at a different moment. 1 second ago, 1 second from now, they're still delicate, held in place by a scaffold of probability. As you move past them, they flicker. Not because you're changing them, because they were never fixed to begin with. You think about yourself, about memory, about how the mind builds the illusion of time through layers of perception and chemical signals. And for the first time tonight, you wonder, if time at the quantum level is this unstable, what does that mean for you? Are you moving forward, or are you collapsing into the memory of having done so? Some physicists propose that time may not be fundamental at all, that it might emerge from entanglement or information flow, a secondary quality, a side effect of correlations. In some formulations of quantum gravity, time doesn't even appear in the equations. It has to be reconstructed afterward, like a story told backward from its ending. You now enter a space labelled temporal echoes. Each panel plays a quantum interaction in reverse, then forward, then back again. You try to tell which is which. You can't. Not without an entropy, not without something to mark the passage. You begin to realise that what you call the past might just be a collection of low entropy memories. Not an absolute place, just a version of now with better documentation. And suddenly you remember the entangled particles from earlier, the ones that twitch together across space. What if they're entangled across time too? Some researchers are starting to toy with the idea that quantum entanglement might extend through time the same way it does through space, that a particle's state now might be influenced by another particle's state in the future or vice versa. Not in a way that breaks causality, just in a way that reshuffles what it means. You pause beside a frame filled with equations. It's labelled simply, "Time is what happens when nothing else does." You don't know whether to laugh or cry. And then you see it. A version of yourself walking in reverse, steps unhappening, breath unbreathed. They fade as you watch, not because they're going away, but because you're remembering them instead of witnessing them. And perhaps that's all time is, not a line, but a layer. You're floating again, only now everything feels hollow, not in a scary way, more like a bell after it's been struck. There's a quiet resonance around you, as though space itself is humming a note just out of earshot. You look around, expecting the usual parade of particles, electrons, protons, the occasional bored-looking photon drifting by, but they're gone. In their place, the universe has left something larger, something more fundamental, something a bit blurrier. You've arrived at the realm of fields. If you were holding out hope that quantum physics would eventually return to tiny billiard balls bouncing around, I regret to inform you, the particles have left the building. Or rather, they were never really there, not the way you think. Because at its deepest level, quantum physics doesn't describe the universe in terms of objects. It describes it in terms of fields. Continuous, stretching, vibrating fields that fill all of space, everywhere, always. Every particle you've ever met, just a localized ripple in one of these fields. A wiggle with a name. You drift into the first field now, wide, subtle and silvery. It stretches in all directions. The sign above it says electron field. It doesn't mean there are electrons floating around here. It means this field exists throughout the universe, even where there are no electrons, but when it vibrates just right in a specific spot. An electron appears, not conjured from nothing, but born from excitation. Each fundamental particle in nature, electrons, quarks, photons, has its own field. That's the big idea behind quantum field theory, or QFT, which is basically the operating system for modern physics. Particles don't exist as isolated nuggets. There are quantized excitations, blips, in invisible, omnipresent fields. like tiny waves that forgot how to spread out. You enter a side room lined with diagrams, each one an attempt to explain how interactions happen in this field-filled universe. A photon doesn't fly from one place to another like a bullet. It emerges as a disturbance in the electromagnetic field. Two electrons repel not by tossing tiny invisible balls at each other, but by swapping vibrations in overlapping fields. Forces become exchanges, exchanges become math, and the math, it's terrifyingly accurate. The predictions made by quantum electrodynamics, one of the first successful quantum field theories, match experimental results to more than 10 decimal places. That's like predicting the circumference of Earth down to the thickness of a single human hair. It's absurd, it's beautiful, it's terrifying. Historians still argue whether the move from particles to fields was an aesthetic decision or a reluctant surrender to the math. In truth, it was both. The old particle model couldn't explain everything, like how forces worked over distance or why particles behaved like waves in double-slit experiments. Fields offered a richer tapestry, a deeper rhythm, but they also forced physicists to abandon the comforting idea of stuff as things you can point to. A projection starts to play on the wall, Richard Feynman scribbling his famous diagrams, little cartoons that represent interactions between particles as squiggly lines, but even Feynman knew those were just visual shortcuts. The reality underneath is less concrete. It's not about things colliding, it's about fields dancing. You reach out to a wall of shimmering light labelled Higgs field. This one's different. It's always on, filling the entire universe like a fog you can't see. Most fields only ripple when disturbed, but the Higgs field is constantly there, constantly interacting. And when particles move through it, they don't glide, they drag slightly. That resistance gives them mass. No Higgs, no mass, no stars, no us. In 2012, physicists at CERN confirmed the Higgs boson, the particle that proves the Higgs field is real. But again, it's not really a particle. It's the tiniest measurable bump in that field, just one way to poke the fog and see it wiggle. A quirky fact floats by. If you could remove the Higgs field entirely, not that you should try, it's estimated that all fundamental particles would become massless. They'd fly through space at the speed of light. Nothing would stick together. You wouldn't be here reading this. Your atoms would unravel faster than your weekend plans. You pass a display marked Quantum Vacuum Revisited. You smile. We've been here before, but now you see it with new eyes. The vacuum in field terms isn't empty. It's just a field in its lowest energy state. But even then, it jitters with fluctuations. That's what those virtual particles are. Tiny blips in the field appearing briefly before fading back. A universe bubbling with ghost waves. And yet, all this complexity, the endless fields, the interactions, the jittering vacuum, still obeys elegant, if dizzying, rules. You float into a room labelled renormalization, which sounds like something you do to your emotional state after a family dinner. In physics, it's the process of making infinities go away. The raw math of quantum fields tends to produce absurdities, divergences, infinite results. Renormalization tames them. It turns chaos into usable predictions. It's tedious, but it works, like ironing a wrinkled universe. You pause by a simple sign. It reads, "Particles are not things, they're events." You sit with that for a while. What you've always pictured, little solid marbles spinning through space, is a useful fiction, a simplification that gets you through the day. But in truth, there are no marbles. There are only flickers in vast, invisible oceans, ripples that act like objects, spikes in probability, moments of structure in an otherwise unbroken medium. And you're a composite ripple, a symphony of overlapping fields, electron fields, quark fields, gluon fields, all vibrating in harmony, temporarily. Because when the ripples stop, you're gone, not because something leaves, but because the pattern stops repeating. You walk again, slowly now, under a dark sky filled not with stars, but with wave functions. They stretch infinitely, overlapping like soft music. Nothing solid, nothing certain, and yet everything still holds. The ground doesn't give way, the air doesn't vanish. Somehow this great ballet of invisible fields creates solidity, identity, gravity, memory. You're still here. Even if you is just a ripple in the right place at the right time, you're not standing anymore. You're falling, or at least that's what it feels like. not in a panicked, screaming down a well kind of way, but a long, slow gravitational pull that tugs at every part of your being, even the parts you didn't know had mass. The walls are gone, the lights are gone, the quantum fields behind you have faded into silence. Ahead you see it, not a door, not a tunnel, but a singularity, a black hole, looming like a punctuation mark at the end of physics. This is where everything breaks, where gravity, quantum theory, and time itself come to blows. Welcome to the domain of quantum gravity. It's no exaggeration to say that this is the great unfinished puzzle of modern physics. On one side you have general relativity, Einstein's masterwork explaining gravity as the curvature of space and time. It's beautiful, it's smooth, it's gigantic. It works perfectly on the scale of stars and galaxies. On the other side you have quantum mechanics, chaotic, jittery, probabilistic, and accurate to within a trillionth of a decimal point at microscopic scales. Each theory is a masterpiece, they just don't like each other. You spiral gently toward the black hole now, not too close, not yet. Around you, the fabric of space-time dips like a trampoline under a bowling ball. According to general relativity, this curve explains everything from planetary orbits to time dilation. And yet, when you zoom in, far smaller than atoms, far deeper than space-time itself, the math unravels. You get infinities where you shouldn't. Singularities that no equation can describe. And worst of all, you lose information, something quantum theory swears should never happen. Historians still argue whether Einstein anticipated this conflict. He certainly disliked quantum theory's probabilistic nature, but it's unclear if he foresaw that his own gravity model would one day need to be reconciled with it. What we do know is that ever since the mid-30s, physicists have tried to merge these two frameworks. So far the attempts have been, let's say, ambitious. You pass a wall etched with the names of contenders: loop quantum gravity, string theory, causal dynamical triangulations. Each one is a bold proposal to quantize gravity, to treat it not as a smooth continuum, but as a grainy, discrete structure made of Planck-scale chunks. Imagine space and time as pixelated, like Minecraft, but with more existential dread. Loop quantum gravity suggests that space itself is woven from tiny loops, like a cosmic chainmail that resists being compressed to zero. If true, it could resolve singularities. Black holes wouldn't contain infinities, just dense, quantized folds of space. The idea is elegant. The math? Complicated, and still very much in development. String theory goes further, saying that particles aren't particles at all, but tiny vibrating strings. Each mode of vibration corresponds to a different particle. Gravity? Just one more note in the string song, and because strings naturally include a graviton, the hypothetical quantum particle of gravity, many believe this theory could unite all fundamental forces under one mathematical umbrella. But it also requires extra dimension, at least 10, maybe. More. Some compactified into loops smaller than atoms, others stretching across unseen realms. You fly through a projection of a Calabi-Yau manifold, a 6-dimensional shape required by string theory. It spins softly, like a jewel designed by someone who's never seen 3-dimensional space, but has a deep appreciation for math-induced nausea. But neither loop quantum gravity nor string theory has been proven. Not yet, and black holes remain the battlefield. You inch closer now to the event horizon, the point of no return. According to relativity, nothing escapes beyond this boundary. Not light, not matter, not even hope. But quantum mechanics has a problem with that. Because according to its rules, information, the specific details of a system, can't be destroyed. It can scramble, it can hide, but it can't vanish. So when something falls into a black hole, where does the information go? This is the black hole information paradox, and it's been haunting physicists for decades. Stephen Hawking originally proposed that black holes evaporate via Hawking radiation, particles generated at the edge by quantum fluctuations, but the particles emitted seem to carry no information about what fell in. Over time, the black hole shrinks and disappears. The information, gone. But quantum physics says that can't happen. You stand now on the brink watching virtual particles flicker at the horizon. One falls in, one escapes. You remember this from earlier, the ghostly handoff that slowly unravels a black hole from the outside in. Hawking's theory was radical but incomplete. More recent proposals suggest that maybe the information is encoded in the Hawking radiation. that it escapes in a scrambled, unreadable mess, like a cosmic capture, but not erased. Others say that the information might be stored on the event horizon in some holographic form. That's the holographic principle, which posits that everything inside a region of space can be described by information encoded on its boundary. In other words, reality might be a projection. You blink at the implications, you might be a projection. The idea finds strange support in the math of black hole entropy. In 1973, Jacob Bekenstein showed that the entropy of a black hole, a measure of how many ways its insides could be arranged, is proportional not to its volume but to its surface area. This runs completely counter to classical intuition, and it hints that the deepest truths about space, time, and gravity may lie not within but at the edges. You finally touch the event horizon. There's no scream, no stretch, just a pause. Time seems to slow, not metaphorically, literally. According to relativity, from an outside observer's perspective, you'd never actually cross the event horizon. You'd freeze in place, your signals stretched into eternity. But to you, you fall right through. No fireworks, no drama. On the other side, everything goes quiet. And here, deep inside the heart of contradiction, you see it. Space and time curled. Quantum fields tangled. Causality muddled. Somewhere, gravity and quantum mechanics are whispering to each other, still working out their truce. You can't hear what they're saying, but you know this much. When they finally agree, it will change everything. Not just physics, but the way we understand what it means to exist. You're not sure how long you've been here. Inside the black hole, or maybe just inside the problem. Time, as we've learned, isn't a loyal companion down here, but now something is forming in the dark ahead. It's not a place, it's not a person, it's a question. The oldest one, the most stubborn one. The one that's been tiptoeing through this entire journey, wearing a lab coat and whispering in your ear. What even is a measurement? You've arrived at the measurement problem. Of all the quirks quantum mechanics throws at us, superposition, entanglement, tunneling, this is the one that refuses to fade. The one that's not just a feature, but a wound in the heart of the theory. Because quantum mechanics is, at its core, a theory of probability, a theory of potential. It tells you what could happen, with astonishing precision. But the moment you actually look, it stops being a cloud of probabilities and becomes a single outcome. It collapses. The math says it must, but no one knows how. You walk now through a hall of mirrors, only these aren't showing reflections, they're showing quantum wave functions. Each mirror displays a particle in full superposition, spread out, undetermined, fuzzed into a blur of maybe this and maybe that. You tap one mirror, the particle resolves, ping, into a point. Another mirror, ping, another decision. But you didn't do anything special, you just observed. So what exactly is a measurement core? Is it a person looking, a sensor recording, a cat meowing, a photon bouncing off a surface? Where is the line between quantum weirdness and classical certainty? And who or what draws it? You pass a sculpture shaped like a Mobius strip with the words observer and system carved into opposite sides. You walk around it once and realize they're the same side. The boundary blurs. Always. The Copenhagen interpretation, which you met earlier, simply tells you to accept collapse as part of the deal. It works, it matches experiment, but it dodges the mechanism. Shut up and calculate, remember? Then there's the many worlds interpretation, which says no collapse at all. The wave function never stops evolving. All outcomes happen in parallel universes. But if that's true, why do we feel like we only experience one? You pass a display titled Wigner's Friend. A thought experiment. In it, your friend is inside a sealed lab, measuring a quantum system. To your friend, the wave function collapses when she observes it. But to you, outside the lab, the system, including your friend, is still in superposition. Has the wave function collapsed? Depends who you ask. This isn't a plot hole, it's the plot. Historians still argue whether this ambiguity is a flaw in the theory or a flaw in how we interpret it. Quantum mechanics has survived every test, every single one, but it's never told us what's really going on when we observe. Some physicists think a deeper theory, yet undiscovered, will explain the collapse. Others suspect the question itself might be meaningless. You walk now into a darker space, no mirrors, no projections, just a soft voice playing from all directions. It recites interpretations like bedtime stories. Collapse. Theories. Maybe wave function collapse is real, physical, objective. The GRW model, for example, suggests that collapse happens spontaneously, randomly, even without observers. Just every so often, a particle decides, I'm done with this superposition nonsense, it collapses, and the rest of reality adjusts. Decoherence-based views. Maybe collapse isn't necessary at all. Maybe decoherence, the entanglement of systems with their environment, explains why superpositions become unobservable. But again, it doesn't answer why you perceive one outcome. Why not both? Why not none? Cubism. A newer view? Quantum Bayesianism. It says the wave function isn't about objective reality at all. It's about your knowledge, your belief. Measurement doesn't collapse the system, it just updates your expectation. The world is real, but the wave function lives in your head. Relational quantum mechanics. Measurement isn't universal, it's always relative. A fact for one observer might not be a fact for another. There's no single story, just stories woven from different perspectives. You pause, let the voices fade. In a side display, a tiny screen loops a single particle being measured, over and over. The wave function, mathematically perfect, evolves deterministically. Then boom, measurement, collapse, randomness. You rewind, play again, and the math works until it doesn't. And yet the results are always right. You step into a mock laboratory, slick white counters, glowing graphs, the hum of equipment. A simplified quantum system is running. You watch an entangled photon pair get measured. One detector flashes spin up, the other spin down. You know the rules, you know the predictions, but the actual moment of the measurement occurs, the instant a possibility becomes a fact. No one here can explain that. A quirky real-world anecdote plays over the speakers. In 2022, an experiment tested Wigner's friend-style scenarios using entangled photons and labs within labs. The results suggest, at least according to the standard interpretation, that different observers can genuinely record different realities, not just disagree on facts, live in separate factual worlds. This doesn't mean truth is dead. It means that reality itself may be observer-dependent in a way we've never faced before. You drift out into a final chamber. The ceiling is covered in floating equations, Schrödinger's equation, describing the smooth deterministic evolution of the wave function. But it ends nowhere. There's no collapse rule in the math. It's added by hand, assumed, a line of code added by users, not the developer. You sit beneath that ceiling for a long while. The measurement problem isn't just unsolved, it might be unsolvable. Or it might be the key to a deeper understanding of reality. A theory that's waiting just outside the edges of what we can measure. A theory not of particles and waves, but of observers and interactions. A world that isn't made of things, but of questions. And you're not just asking them. You are one. You're floating through fog now, but it's not made of vapor. It's made of question marks. Soft, luminous, weightless. Everything you've touched, learned, collapsed, or confused is hanging in the air around you, circling slowly like curious birds that aren't quite sure if they're supposed to be here. This is the edge, not of space, not of time, but of comprehension. You've reached the final layer of the quantum realm, the place where even the definitions start to unravel. This is where reality might be optional. You stand, if stand is still the right word, at the end of the trail, and the signs are gone, the diagrams have stopped. What remains is a strange kind of openness, like walking into a room that hasn't been built yet. And here you have to consider something radical. What if everything you think of as real, particles, space, time, even the concept of objects, is just a byproduct of quantum rules playing out in an elaborate, probabilistic dance? Not real in the way rocks and sandwiches are real. Real in the way stories are real, structured, coherent, believable, but still at their core stitched together from rules, approximations and choices. You turn slowly and the fog parts to reveal what looks like a globe. Not Earth, but a strange spinning sphere filled with overlapping wave functions, like threads in a tangled ball of yarn. It pulses with interference patterns. It's a model of the universe, but not as a collection of particles, as a state vector, a massive, evolving quantum object that contains all possible configurations at once. It doesn't change in time. It is time. It doesn't move through space. It contains space. Some interpretations of quantum cosmology suggest that this universal wave function doesn't need observers. It evolves on its own, calmly, mathematically, without anyone to measure or collapse it. That means reality. This entire adventure might not be happening in the traditional sense. It might just exist, like a novel that's never opened. All outcomes written, none experienced until someone peeks inside. You drift close to the globe and place your hand near it. It reacts, not to your touch, but to your presence as an information node. You're not measuring anything. You are the measurement. The observer, the observed, the record, the collapse, all looped into one self-referencing loop. Historians still argue whether the wave function is real, ontic, or just a tool for predicting outcomes, epistemic. But in recent years, experiments and debates have nudged the needle. More physicists are entertaining the idea that quantum states might be more than math. They might be the bones of reality itself. But even reality needs a rebrand down here. You walk through a corridor labelled emergence. On the walls, theories that suggest space and time aren't fundamental ingredients. There are emergent properties. The world isn't built from things, but from relationships. Entanglements, correlations, quantum interactions that, at scale, start to look like space. Like clocks, like particles, but they're just the surface, the echo of something deeper. You pause beneath a banner, "It from Qubit," a phrase coined by physicist John Wheeler, suggesting that it, the stuff of the universe, comes from qubits, quantum bits of information. Reality is information, not atoms, not fields, not even strings, but binary choices entangled across scales. This isn't science fiction, it's being tested. Ideas like the ADS-CFT correspondence in string theory suggest our 3D universe could be a kind of holographic projection of a 2D quantum field. Yes, holograms again. The matrix comparisons are unavoidable, but it's more than metaphor. It's math, verified, peer-reviewed, slightly maddening. And here comes the most humbling twist. If space, time, and matter are emergent, then the foundational layer of reality may be nothing like anything we can imagine. It may not involve shape, or cause, or energy, just a sea of probabilities and correlations. A framework that simply is, and from which everything else, your thoughts, this room, the echo of a cat that may or may not be dead, arises as a statistical inevitability. You pass through a chamber of ancient philosophical graffiti, quotes carved into the walls like fossilized doubt. To be is to be perceived. Berkeley. What we observe is not nature itself, but nature exposed to our method of questioning, Heisenberg. The universe is under no obligation to make sense to you, Tyson. It's tempting to call this the end, but you know better. This isn't a conclusion, it's a horizon, like the edge of a black hole or the surface of a quantum foam. Just because you've reached the end of your understanding doesn't mean the world stops humming. You step through one last curtain of light and find yourself in a final room. No displays, no machines, just a chair, a cup of tea, and a notebook titled Your Reality, Draft 1. You sit, and for a moment it feels like you've circled back to the beginning, because in a way you have. Everything that quantum mechanics has shown you, uncertainty, superposition, entanglement, collapse, decoherence, emergence, it was never about escaping reality, it was about redefining it. Peeling back the assumptions, removing the labels, letting go of the need for firm edges. Because down here, reality isn't a solid wall, it's a probability cloud. And you've always been part of the system. Just one more ripple in the wave and you're still now, not stopped, just still. Like a pendulum at its highest point, suspended in possibility, no longer swinging but not yet falling. Around you, the fog has thinned into something softer, gentler, no longer a mystery, demanding answers, but a presence whispering permission to let go of the question. There's no chart left to follow, no particle trails, no collapsing wave functions, only a gentle suggestion to breathe and let the last echoes settle. Quantum physics doesn't end with an answer, it hums with a question that rewrites itself every time you try to read it aloud. That's its beauty, and its burden. You're not here to conquer it, you're here to wander through it, to sit quietly at the edge of its vast probability sea and know, just for a moment, that your mind brushed against the rules that make stars burn and atoms dance and memories fade and return. Let that feeling stretch, let it soften the noise of the day. Whether you understood everything or nothing, your attention brought it to life, just as it brings life to every electron's path and every cat's unspoken fate. You are the observer, but you are also the observed. A ripple in the field, a brief collapse in an infinite function. So close your eyes now. Let time lose its shape. Let your breath sync with the rhythm of whatever world you've collapsed into. There's no rush to explain it, only the need to rest, and maybe, just maybe, dream in superposition.